The next type of learning problem is unsupervised learning. Here, the model learns on a dataset that has no labels, and instead it just learns what features and patterns are present in this unlabeled dataset and uses these patterns to solve information problems. For example, we might train a model on a bunch of images of fish that don't have labels, and then the model would learn the types of visual patterns that tend to be present in images of fish. And then later, we might give the model an image where there's a missing patch to the image, and then ask the model to predict what are the visual patterns that are most likely to be suitable for filling up this missing patch. So let's look at an example of unsupervised learning by returning to our dog example. So remember, for supervised learning, we had labeled images of cats and dogs, and our supervised learning model was supposed to predict whether an image was of a cat or a dog after being trained on this labeled data. Now, an unsupervised learning model can also be used to learn how likely an image is to be of a dog. However, the unsupervised model learns this structure without any labels. It does so by experiencing a training set made entirely of dog images, and after seeing many examples of dogs, it will start learning what are the prominent characteristics of dogs, what are dog-like patterns that tend to be present in these images, and then it would learn what types of images were more common for dogs versus not. So we train our unsupervised learning model by giving it lots and lots of images of dogs that do not have labels, and we do not tell it explicitly this is a dog versus not a dog. We just show it lots of images of dogs. And the unsupervised learning model's job is to learn what patterns are present in this data set and keep track of how likely different patterns are. And because our training data is entirely a sample of dogs, the data itself will naturally have in its distribution images that are most dog-like to be most prominent, and very few images that are not dog-like. So, for example, it will rarely show something like this that's dubious whether it's a dog or not, and it would never show something like this, picture of a cat. After learning how likely different features are to be features of dogs, then when given a new image, the unsupervised learning model can then output a probability corresponding to how dog-like is this image. So we can see here that very similar information processing problems can often be solved with either supervised or unsupervised learning. We've seen examples of both supervised and unsupervised learning models predicting the probability of an image being a dog. However, while the format of the output is similar between these two models, they are customized to slightly different problems. The supervised learning model was trained on labeled images of dogs versus cats, and it knew the category had to be either a cat or a dog. So if it was likely to be a dog, then it's unlikely to be a cat, and vice versa. So because the supervised learning model was also learning to categorize cats correctly, it would probably be pretty accurate in classifying a cat image like this one. It would say that it's very likely to be a cat, and this is equal to saying it has a very low probability of being a dog. In contrast, if the unsupervised learning model saw a cat, it wouldn't have been trained to distinguish cats and dogs per se. It would only say how dog-like this image of a cat was. And it's quite possible that an unsupervised learning model that's only been trained on pictures of dogs would see this picture of a cat and think, well, it's still kind of dog-like, and give it a fairly high probability of being a dog. You might wonder how the unsupervised learning model evaluates its performance if it doesn't have labeled training data. Well, the unsupervised learning model still has training data even if it doesn't have labels. So the unsupervised model gets evaluated not on its accuracy of predicting labels, which it doesn't do, but on its accuracy of predicting the patterns in the data. Many unsupervised deep learning models are also generative models. And this means that the model, which predicts a probability for a piece of data, can also be used to generate examples of their training data. So here, you could ask the model to generate an image of a dog, and it might come up with something like this. This image is generated from a real unsupervised deep learning neural network trained on dog images. The model is a type of unsupervised learning model known as generative adversarial networks. Here, you can see that the model has learned some visual dog-like features, but it's not quite right. It seems to have too many heads and maybe too many feet. And this is because the deep learning model was learning based on its own patterns and coming up with its own features. It wasn't told explicitly that there's such thing as a head and a foot and how many of these things there should be. But instead, it found head-like and feet-like patterns nonetheless associated with this training set of images. Generative deep learning models have made great advances lately, and notably, researchers at NVIDIA have used these models to create faces that are impressively realistic. Every one of these facial images was generated from a deep neural network. Another example for seeing how supervised and unsupervised learning can be used for similar problems is language learning. Language learning is a good example for demonstrating how the goal of learning is to be able to generalize beyond what we've just been exposed to. Successful language communication requires generalization. In order to communicate, we're always hearing and saying new sentences that we've never said ourselves and never heard before. But yet, we're pretty much always sure that we know what the new sentences we hear mean, and that the new sentences that we say will be understood by others. For example, many of you probably haven't heard someone say the exact sentence, "I've never shouted this exact sentence before." Even if you've never heard someone say that exact sentence, you understood what I'm saying. This is an example of our need to be able to make generalizations beyond our past experience in order to communicate with language. We're always saying and hearing new sentences that we haven't exactly encountered before. Let's consider a model whose purpose is to determine whether a sentence is grammatical or not. This model needs to be able to take a new sentence that has never encountered before and predict whether the sentence is grammatical. We can use either a supervised or unsupervised learning model for this task. The two different types of models would receive different types of training data and have slightly different learning goals. The unsupervised model would learn grammaticality of sentences by being given lots and lots of examples of grammatical sentences, and it would learn what patterns there were in this group of grammatical sentences and how often different patterns occurred. It would learn to generalize and predict the grammaticality of new sentences based on the patterns it had learned from the set of grammatical sentences it had been trained on. An example of a human undergoing such unsupervised language learning would be if you were learning a new language and you never got told which sentences were grammatical or not, you just wandered around listening to native language speakers and picked up patterns. Maybe this is like if you were learning a foreign language by watching TV shows, or if you were a child learning a language for the first time and you were listening to the adults around you speaking and you don't get any feedback on what is grammatical. You're learning what was grammatical purely by picking up the patterns in the grammatical sentences spoken around you. You're never told what is correct and what is not. And so you eventually learn to speak and hear, having experienced so many native speakers speaking the language correctly, and you're able to judge whether new sentences are grammatical versus not. Here, you're acting like an unsupervised learning model. In contrast, imagine you were learning a new language and you heard both grammatical and ungrammatical sentences, and you got feedback for every sentence about whether it was grammatical or not. As you experience more and more sentences, for each of which you are told whether it's grammatical or not, you start building a model of the type of sentence that is grammatical versus the type of sentence that is ungrammatical based on all your feedback. Both supervised and unsupervised models are learning to generalize the structure they've learned in order to predict the grammaticality of new sentences. Both types of models might have similar predictions for many sentences. However, there will be situations where they differ in their judgments of grammaticality because the supervised learning model was learning rules based on positive and negative labels of grammatical and ungrammatical sentences, whereas the unsupervised learning model was learning patterns from only positive examples of grammatical sentences, and therefore the different models could sometimes come to different conclusions about the grammaticality of new sentences. When discussing supervised learning, which was learning from labeled data, I had talked about how for image processing models, the 1 million labeled images offered by ImageNet was often used to pre-train more specialized image recognition models. In the domain of language understanding, we don't have the equivalent of ImageNet. Language understanding is the domain where there are so many different problems to solve, like so many different concepts we'd want our model to recognize on so many different topics, that we often don't have enough labeled data for each of these topics. For example, say we want to build an AI that is a healthy eating coach that you can talk to in any situation when you had an unhealthy eating temptation. And the coach will try to talk you out of making an unhealthy choice. For the coach to be effective, we would need it to be able to understand the situation around eating moments based on your natural language description of what's going on. So we'd need to train a language understanding model to recognize the many different concepts related to eating, including what type of meal it is, what location you are in, whether you are being social, and all the different motivational challenges associated with the psychology of healthy eating. So to have a model that could recognize all these concepts requires training a supervised learning model on a data set of many, many sentences that have been labeled with each of these concepts relevant to the psychology of eating moments. If we were training such a model from scratch, we'd need a very large number of labeled sentences to get a language understanding model to accurately recognize the relevant concepts from someone's natural language description. Getting such a customized labeled data set for a specific topic domain, like healthy eating, for example, is a challenge. However, this process can be made easier with unsupervised pre-training. Because what we do have is we have huge unlabeled data sets of language. And so these are just big corpuses of language text, such as the book corpus, which are 7,000 unique books in the English language, or Wikitext, which is a huge corpus of all Wikipedia articles that have good ratings, and many other corpora like these. And these text datasets have on the order of hundreds of millions to 1 billion unique word tokens and sentences. But they're unlabeled. They don't have concepts associated with them. So here is where pre-training with an unsupervised learning model is very useful. Because we can train an unsupervised learning model on these huge data sets of unlabeled language text and use the language patterns found as features that we can then use for solving specific language understanding problems that require labeled data, but for which we only have a small labeled data set. If we pre-train an unsupervised learning language model on a large unlabeled data set first, we can greatly improve performance on a language task that requires supervised learning, with much fewer labeled training examples. A recent study showed the benefits of this for text classification, which is a supervised learning task that requires training data of many examples of text labeled with their corresponding categories. This study showed that if we do pre-training using an unsupervised learning model on unlabeled text data first, on the subsequent supervised learning task with only 100 labeled examples, we could achieve an accuracy on text classification that would have otherwise required up to 20,000 labeled examples without this unsupervised pre-training. So, unsupervised learning, in addition to being a very important learning approach on its own, is also a very useful approach for pre-training supervised learning models to prepare them to solve problems for which we have limited labeled data.